Okay, we're here for, what is this, the third lecture in the course, and I'm trying to learn better how to use my, my pen and my remote tablet. I still got a little bit of wigglies in it, and I've been trying to position my hand so it doesn't wiggle as much, so we'll see how it does. So I'm going to share my screen. If I can find the place to share the screen. Okay, there's the share the screen, and hopefully everybody can see this. If you can't see that, if you're not here, raise your hand. No, if you, hopefully you can see that. Nod your head if you can. Okay, you can see it. Okay, so we've been talking about the Fourier transform and reviewing some of the properties. These properties for are stuff that we had as an undergraduate, and it's kind of review of some of these things. We already have looked at the continuous time Fourier transform, the derivative theorem. We proved that. And then, let's see, before that, we had convergence, and we had Parseval's theorem for the Fourier series, and we studied things in the Fourier series, didn't we? So convergence, of course, is haunted by Gibbs phenomenon. There's nothing you can do about it, but it's still something that's interesting. It's something that we mitigate all the time. So we derived the derivative theorem last time, which says that if you have a derivative, then you multiply the Fourier transform by J2 pi u. And it turns out that the magnitude of J2 pi u, if you just look at the magnitude of the spectrum, okay, I can do this. I think I'm going to try it down here. I think I got better results last time. Let's look at this. This is a very interesting result. This is this is just the magnitude, and we're just going to look at the magnitude of that. And the magnitude of the Fourier transform, we said before, was as follows. If we had a spectrum, a signal which is x of u, and we multiplied by J2 pi u to the n, it's multiplying by, I don't know, some sort of parabolic sort of thing. But the important thing to see is that the DC term gets wiped out, and all of the high frequencies are amplified. So therefore, derivatives are a good way to perform edge detection. So edge detection is one way to look at the derivative theorem. Let's look at the Shift Theorem. The Shift Theorem is kind of interesting. The question is if you listen to a recording today, say an x of t, and then you listen to the same recording tomorrow, say x of t minus tau, where in this case tau is 24 hours, you'd expect the spectrum to be the same, wouldn't you? I mean, it's the same, it's the same song, but it's just delayed 24 hours. And so if you recall, we use the notation x of t has a Fourier transform of capital X of u. And this was our shorthand notation for the Fourier transform. The Shift theorem says that the Fourier transform, if you play the record tomorrow, if you play the song tomorrow, you get exactly the same spectrum, except the spectrum is accompanied by a phase delay, e to the J2 pi u tau. So the proof of this is pretty simple, and this proof is not in the book. For some reason, I left out the Shift theorem when I wrote the book, but we can see that x of t minus tau is going to have a Fourier transform of the following. It's going to be the integral from minus infinity to infinity of x of t minus tau times e to the minus j 2 pi ut. So that's going to be the definition. That's just the definition of the Fourier transform. I'm going to write this in a little bit different way just to make a point here that is important in manipulation of things. That is the same thing as x of, instead of using the t variable, we're going to use the c variable. Whoops. Yeah, we're going to use the c variable here. No whoops. I goofed there. X of c minus tau e to the minus j 2 pi u c dc. This c is referred to as a dummy variable. What's a dummy variable? Well, it doesn't matter what we integrate with respect to. If you think about it, think of the following. We have some function here, z of t, and we have a z of t which looks like this. And then we have a z of c, and it's going to be exactly the same function. So I'm going to do my best to draw the same function. Supposedly, those two are exactly the same thing. Now we ask ourselves, what is the integral of z of t over all time? Well, it's this area, right? Is that the same as the integral over all of c? Yeah, the functions are exactly the same. So it doesn't matter whether this variable is a c or a t. As if we're integrating over it, it doesn't matter which one we choose. So therefore, sometimes it becomes nice to use a dummy variable because the dummy variable is just a placeholder. In fact, we could, little levity, we could put smiley face here. That's supposed to be a smiley face. And a z of, man, I'm terrible on my smiley faces here. A z of smiley face. And the integral over smiley face is going to be exactly the same, isn't it? It doesn't matter what that variable is. It's a dummy variable. So getting back to the derivation down here, this derivation, this integral is exactly the same as this interval. And I do that because I want to reintroduce the variable of t, because I like t and it's nice and friendly with me. And I'm going to set t is equal to c minus tau. So therefore, tau is a constant. That's our delay. That's our 24 hours, if you will. And dt then is equal to dc, since the constant tau goes away. So we're left then with x of t minus tau is equal to the integral. Now, before we integrate it over c, now we're going to integrate over t again. And c minus tau is equal to t, so this becomes an x of t. And then we have an e to the minus j 2 pi u. And let's see, what is c? Well, from here, c is equal to t plus tau, right? So this is, instead of c, it's t plus tau. And we are integrating over t now. You'll notice something here, that that the integration is over t. So therefore, anything not a function of t, we can factor outside the integral. So we get an e to the j 2 pi u tau times the integral over t of x of t times e to the minus j 2 pi ut dt. So we can break this up into the factor, of course, of two exponentials and then factor one of them outside. And we see wonderfully that this is the definition of the Fourier transform, 2 pi u tau. And this integral is the Fourier transform of the signal that we're talking about. So therefore, we have derived the shift theorem, because what I just wrote here was what I promised up here, right? So that's the shift theorem of the Fourier analysis. So it makes sense, because if you delay the spectrum, or if you delay a signal, you should have the same spectrum, except that it's delayed by a linear phase shift. Let's look at the convolution theorem. You're all familiar with this, and the convolution theorem is that the convolution of two functions, x of t times h of t, is given by this integral. Convolution, you know, is foundational for system theory. We're not going to be talking about system theory in here very much. Well, and not at all, in fact. But usually, if you have a linear time invariant system, and you can characterize the linear time invariant system by an impulse response, and this impulse response is h of t. And that's kind of cool because linear time invariant systems are really nice because you don't have to sit around and figure out what it does all day. You just measure the impulse response. You stick h in your pocket and you're able to go home, and then anybody gives you an input and you say, I can tell you what the output is. Give me the input. I'll just convolve it with my impulse response and I'll give you the corresponding output. And that's what the motivation is behind the convolution theorem. If you know, when you take classes in Fourier analysis, the first thing they do is they torture you with all this flip and shift, and you have to do all these convolutions. Then they teach you that an easier way to do it is to take the Fourier transform of each of the components in convolution, multiply them together, and then inverse transform, and that gives you the exact same result. And that's what this result is. That x convolved with h of t in the Fourier domain is x convolved with h of t in the Fourier domain is x times h. Now we can prove that because x convolved with h, well, we don't want the equal to, we want it Fourier transforms to the integral over t of x convolved with h times e to the minus j 2 pi u t dt. That's the definition of the Fourier transform. So we see that if we were to write this out in longhand, which we need to do, this is the integral over t, and then we get the integral over tau. Because you notice this integral, this convolution integral up here is an integral over tau. We got to be careful not to mix up our variables of integration. And now we're going to do something which we can always do. We're going to switch the order of integrations. In this course, you can always switch the orders of integration. If you're in a math class that's very particular on things, you got to worry about whether you can switch integration or not. But I have the theory that if you do switch integration and you're not supposed to, the math is going to tell you something. At least that's been my experience. So we're going to switch integrations, and we're going to integrate over tau first. Then we're going to integrate over t. And we integrate over t, we get h of t minus tau times e to the minus j 2 pi u t dt. So that becomes the integral over all of the t variables. And then we're left with the x of tau out here. So we switch the order of integration, so we get this response. This is really great because now we can apply a theorem that we've seen before. What is this recognized as? This is recognized as the Fourier transform of a shifted h. It's the Fourier transform of a shifted h. So therefore, we can apply the shift theorem. We can apply the shift theorem, and we get h of u times e to the minus j 2 pi u tau. So that's what the stuff inside the brackets is. And then we have the x of tau times the d tau. This is really nice because now we can factor the h outside, and we factor the h outside, and we get h of u times this integral. And this integral is recognized as the Fourier transform of x. So look, we are home. We have proven the premise that we have multiplication in the frequency domain. Relatively straightforward. So we have down here, what we promised up here. That the Fourier transform of the convolution is equal to the product in the frequency domain. This, of course, is very important way to characterize linear time invariant systems. Here's the inversion theorem. We stated the inversion theorem without proof. Remember, this was the Fourier transform, and this was the inverse Fourier transform. The Fourier transform gets you from x of t to the frequency domain. The inverse transform gets you from the frequency domain back to the time domain. Now, we've stated this previously. We're not going to prove it now, because in order to prove it, we have to have something called the Dirac del. So we will save this proof for later, because we don't have the tools to prove it yet. But the beautiful thing I would re-emphasize again is by using u, which is cycles per second, there's no 1/2 pi's in the inversion. And that's always nice, because you'd like to minimize the bookkeeping, and this certainly does that. Now we have the duality theorem. The duality theorem takes advantage of the fact, if we go back here, that the Fourier transform up here looks a lot like the Fourier transform down here. The forward Fourier transform and the inverse Fourier transform look very, very similar. So therefore, you can have a duality here, and that's what the duality theorem says. I think you all know, for example, that if you have a rectangle function, you'll remember this from undergraduate. If you have a rectangle function, you know what a Fourier transforms into, right? It Fourier transforms into a sine x over x function, which kind of looks like this, right? Hopefully you remember that a rectangle function Fourier transforms to a sine x over x. So we would expect, because of the duality theorem, that a sine x over x that was x of t would Fourier transform into a rectangle function in the frequency domain. So therefore, the cool thing about the duality theorem is every time you have a Fourier transform, you double down. You have two Fourier transforms. If a rectangle transforms into a sine x over x, then you know a sine x over x transforms into a rectangle function. And here is up here is the little details you need. If x of t transforms to x of u, if the rectangle transforms to the sine x over x, then the sine x over x transforms to the rectangle, except what? There's a transposition, there's a shift. There's a rotation around the y-axis. So except for that, it's pretty straightforward, and this lets you double all your Fourier transforms that you use. The duality theorem. How we doing so far? Any questions at all? Okay, don't forget, you're welcome to interrupt me. The scaling theorem is relatively important. Now, the scaling theorem is something I think a lot of people get wrong when they first think about this. If you have something which is x of t, say x of t, which looks like this up here, And say this goes from 0 to 1. I'm just sketching something. And you'll notice in these lectures, I'm trying to appeal to your, geometrically, because geometrically is a really good way to think. And let's say this has a height of 1. I'm going to take and I'm going to kind of spread this out. And this goes over to, instead of 1, it goes over to m. Now, the question is, m is for magnification. That's how much it's magnified. We're going to keep the top exactly the same thing, exactly 1. So we're taking this function and we're stretching it out. The question here is, what is this? Is this x of t over m? Or is it x of mt? Let's have a vote on it. How many think it's x over tm? No one. How many thinks it's x of mt? You guys are so non-committal. Nobody's voting. Okay. Okay, if I had a proverbial gun to your head, which one would you vote for? How many would vote? Just raise your hand of x of t over m. Okay, wow, x of mt. Okay, well, it's x of t over m. And I tell you, you know, it's against your intuition. It's against your intuition, because I would expect it to be x of mt, but this is not what it is. So here's what happens. This is the scaling theorem. It says that if you have a function in one domain, say an x of t, and it has a Fourier transform of x of u, the scaling theorem says that if you shrink this, now notice this is x of a of t, so therefore if a is greater than 1, we're actually shrinking it, we're actually making it smaller. So if we have an x of a of t, we come down to here, then that is going to Fourier transform to something which is more spread out. So therefore, if this is compressed by a factor of m, this is going to be magnified by a value of m. So this is going to be x of u over a. A is the magnification here. And notice there's an amplification here. It's 1 over a. That's a little fudge you have to put in here. You notice right away that I make my a's two ways. I make them as a typewriter a and I make them as a cursive a, and they're the same. I've long time ago quit trying to be consistent. So both of those correspond to an a, if you will. So again, shrinking in one domain corresponds to expanding in the other domain. This has manifestations all over the place. One of them is, you've heard of Heisenberg's uncertainty principle, wherein this denotes the certainty of the location of a particle, and the Fourier transform, believe it or not, by the magnitude squared of the wave function, corresponds to the uncertainty of the momentum, or the uncertainty of the velocity, if you will. And the more certain you become about the position, the more uncertain you become about the location. So if you're interested in physics, that's one of the places where Fourier analysis rears its head. And we know this. We know this intuitively also, because we have a sinusoid, and we know that the sinusoid has a Fourier transform. We don't know this yet, but it has a Fourier transform of, say, some frequency. Say f naught as a function of u. What happens if we increase the frequency? Boy, that's the worst sinusoid I've ever seen in my life. Okay, but you get the idea. We're taking this sinusoid and we're squeezing it. We're making it smaller. So what do we have to do over here? We have to make this bigger, don't we? So if we take that sinusoid and we make it bigger, then our frequencies have to be way out here by whatever factor we squeezed the sinusoid in, right? So these frequencies have to be much higher. So we see an intuitive manifestation of the scaling theorem here. Again, if we have a sinusoid which has certain frequencies, and we have another higher frequency sinusoid, this higher frequency sinusoid can be thought of as that slow frequency sinusoid, kind of pushed together, scaled together. And the scaling theorem says that the Fourier transform must be erased, or not erased. I was having two thoughts in my head. The Fourier transform must be expanded. I was thinking about erasing this, and I don't know if I can. I guess I can. Okay, good for me. So that's the idea of the scaling theorem for the Fourier analysis, is that if you make things bigger in one domain, if you amplify, if you scale them, if you make them larger in one domain, you're going to make them more pastas. I have no idea where that came from. Uh-oh. I erased part of the original slide, and I don't want to do that. Okay, well, that's probably good enough. How would you prove this? Well, you would prove this as you do for anything. All of these proofs in Fourier analysis have to do with using the proofs, using definitions, and using changes of variables. X of AT here, we know has a Fourier transform of X of AT, e to the minus j 2 pi ut. Now, if we look at that, we can see immediately that we need to manipulate this to look more like a Fourier transform. So what we're going to do is we're going to use a new variable substitution. Let C is equal to AT, which means that T is equal to C over A, right? And so this is equal to the integral of X of C, e to the minus j 2 pi u. But what is C? C is equal to A times T, right? So DC, so that, well, that's the first thing we do is AT here. And so we say that DC is equal to A dt. Now there's a, okay, so no, that's okay, A dt. Wait, am I doing that right? DC, this should be A, C is equal to AT. I got this wrong. This should be a C, and this should be DC. So dt is equal to 1 over A times dt. And so we were left with the integral of x of C times e to the minus j 2 pi u. But now we're going to lump the A with the u. Did I get that wrong? I did get this wrong, didn't I? Two pi u, this should be t, but what is t? T is C over A. I screwed that up. So I have a 1 over A, and then what is left? What is left is exactly the Fourier transform. It's exactly the Fourier transform, but instead of u, we have a u over A, right? And so this is equal to 1 over a times the Fourier transform, but the Fourier transform is not a function of u. The Fourier transform is a function of u over a. That's the world's worst E. This is the scaling theorem, almost. It's almost the scaling theorem. Up here we have an A, right? We have an A, but we have more than an A. We have a magnitude of A. Where's our magnitude come from? There's no magnitude down here. Well, let's go back in our derivation and kind of see if we can figure out what's going on here. Notice that this integral is from minus infinity to infinity, right? And when we make the substitution, C is equal to AT, we have to ask ourselves in the integral, if T is equal to minus infinity, what is C equal to? Well, C is equal to minus infinity only if A is positive, right? So this becomes minus infinity to infinity under the assumption that A is positive. And everything follows here. So what we've done is we've derived this result, but A must be positive. Well, what happens if A is negative? Well, if A is negative, then this goes from infinity to minus infinity, doesn't it? If A is negative, this goes from infinity to minus infinity. And we can switch around the integral limits by doing what? Shifting the sign of the differential. And that's what we do. But by shifting the sign of the differential, we get the magnitude of A. Now, that's a little bit tricky, and I invite you to go over it, but the requirement that we have 1 over the magnitude of A is necessitated by A either being positive or negative. We have to go through essentially 2 different derivations, one for positive A, which we've done, and if we go through it for negative A, we find out that it generalizes to this expression for all values of A, both positive and negative. So that's where the magnitude comes from. Any questions on that? If not, I'm going to enjoy the hiatus by a fresh cup of brewed coffee. Now, there's a whole bunch of different Fourier transform theorems, and we've just gone through probably the most commonly used. In the book, Handbook of Fourier Analysis, written by yours truly, there is a table of all sorts of Fourier transform theorems. We've just done the scaling theorem. We did the shift theorem. There's a modulation theorem. Now, look at the shift theorem. It says if you shift something in the time domain, you multiply it by e to the minus j in the frequency domain, right? Well, the dual of that is you have something times e to the j in the time domain. That means you shift it in the frequency domain. So the so-called modulation theorem is the Fourier dual of the shift theorem. If we shift in one domain, we multiply by e to the j, a linear shift in the other domain. If we linear shift in the time domain, well, it means we do a frequency shift in the frequency domain. And we know this, for example, in amplifiers by heterodyning baseband signals up into high frequencies. What do? For AM modulation, we multiply it by a cosine. This is the same sort of thing. We're multiplying it by a e to the j. Now, one of the things that we did is we had the scaling theorem and the shift theorem. I kind of like this because if we scale then shift, then this is one theorem that we can look at. Notice that this has both the Shift Theorem and the Scaling Theorem built into it at the same time. And it's very different from this theorem. This is the scale then shift. So you scale the thing, then you shift it. That's different. The operations don't commute. If you shift and scale, that's not the same thing as scaling and shifting. They're two different, the operations are not commutative. And so if you have the shift then scale, you get another Fourier transform. So this one combines both the Shift Theorem and the Scaling Theorem, which is kind of nice. Here's the Derivative Theorem. Derivative Theorem that we have talked about. We have not derived the Integral Theorem. We have not derived the Conjugate Theorem. And this is pretty simple. If you have a complex signal and you do a complex conjugate in the time domain, what do you do in the frequency domain? You do a complex conjugate and a transpose. Transpose means you shift it around the y-axis. And there's a number of other interesting theorems. Here's the Convolution Theorem, which we just derived. And there's some other theorems that we have not talked about, but we have talked about the Fourier series. The Fourier series is in this table also. That if we have a Fourier series, something which is periodic in the frequency domain, that will correspond to a bunch of deltas in the frequency domain. We haven't defined what we mean by a delta yet, but we will very soon. And then there's the sampling theorem, and this is one of the very important consequences of Fourier analysis, the so-called sampling theorem. So you can see we have a number of different theorems. As you see in the upper left, this is on page 15 of your book, in case you need to refer to it. Well, let's then talk about some continuous time Fourier transform pairs. We've done a lot of stuff on theorems, what happens when this goes to this, but we haven't done any Fourier transform pairs. We haven't talked about a rectangle Fourier transforming to a sin x over x, for example. Well, what do we do in such cases? We need to sit back and we need to define them. And you're going to see that we're going to define them very carefully in order to minimize the bookwork that we need to use in order to keep track of Fourier transforms. Everybody has heard of the Dirac delta. Now, I call it the Dirac delta. I think that maybe you've heard of it as the impulse function as an undergraduate, but it's a Dirac delta named after the famous physicist Dirac, who really liked it. Now, the Dirac delta, this is a misnomer. It's not really a function. In fact, if you go over to the math department, they will say, no, this is not a function. It's not a function because you can see it's the limit, and you've seen this before, it's the limit of this rectangle as a goes to infinity. We have a rectangle of width 1 over a and a height of a. So no matter what the value of a is, this is going to have an area of 1. And we take the limit as a goes to infinity. So as this thing squeezes together and pops to infinity, we can think of that as the Dirac delta function, but it isn't a function because you're not allowed to have functions that are infinite at different points. So for years, the mathematicians didn't like this. So they finally came up with a sophisticated treatment of this called distributions. And they would call this a Dirac delta distribution. It isn't a function, but it's a distribution. Nevertheless, the intuitive mileage that we get out of this is enormous. And I think as engineers, and I believe that the physicists would agree, we like to treat this as a function with very special and wonderful properties. So that is the Dirac delta. Now, the Dirac delta doesn't have to be always a rectangle. It can also be something like a triangle. Man, my drawing is going terrible here. Okay, if this is a triangle and this has a width of 2a and this has a height of a and this is centered at the origin, I think if I have that right, this always has an area of 1. Would you agree? Now, just like over here, we could take the limit of this and have it approach a Dirac delta. We could also take this function in the limit and call it a Dirac delta. In fact, there's a whole bunch of functions that we can take as a limit and call a Dirac delta. I'm going to give you some homework on that, but you can see that there's lots of different definitions that we can indeed have. So this is just, by the way, an intuitive definition. This is the way that we as engineers like to think about the Dirac delta. The important thing, it has zero width, infinite height, and it has 1 as its integral. It has an area of 1. Now, let me ask you this.
Wouldn't it be 2 over a, the basis of the triangle?
Well, let's see. You think it'd be
2 over a.
Oh, you're right. I'm sorry, 2 over a. Yeah, in other words, yeah, it would have an area of a squared. Thank you, Glauco. You're exactly right. Now, you can see the integral, this is one of the properties of the delta function. The integral over a delta function, say from minus epsilon to epsilon, is equal to what? 1, right? Because it doesn't matter what a is, it's going to have an area of 1. So even in the limit, this thing is going to have an area of 1. Even in the limit, this is going to have an area of 1. So let me ask you another thing. What do you think the integral from minus c to c of, whoops, delta squared is? Anybody take a hazard guess?
Still just 1?
No. You'll notice that if we square the delta function, that's like taking this function, squaring a, right? And this has an area of a, so the area under the square of a delta function is equal to an infinite. Which means that delta functions don't exist. They only exist in the figment of our imagination. If we had a current, which was a true Dirac delta function, it would set up an infinite magnetic field instantaneously, and it would permeate the universe and it would collapse, right? Because infinite is really, really big. So therefore, in practice, we don't use delta functions. If we get something which is kind of nice and spiky, we say that's pretty close to a delta function. But its analytic mileage is so incredible that we really like to use the Dirac delta. A very important property of the Dirac delta is its sifting property. And in fact, this is the way that the mathematicians, as I understand, define it. They say the delta function, or the delta distribution, is this function delta of t minus tau, that when you substitute it in this integral, that you get x of t out. So you can see why it's called a sifting property, because it takes an x of tau and it sifts out the x of t at the point. Now, this is not too difficult to appreciate. Let's look at, first of all, delta of t minus tau. Notice we're integrating over tau here. So let's make sure that we're integrating over tau. So x of t minus tau is going to be a delta function, which is centered at tau is equal to t. Now we're going to multiply this by x of tau. So here's x of tau. So when we multiply these two functions together, we get 0 everywhere, except where the delta function exists. And what's the value at the delta function? The value at the delta function is x of t, isn't it? So I maintain that this is the same thing as the integral from minus infinity to infinity of x of t delta of t minus tau. Because right here, we see a sifting happening, right? We see that this delta function sifts out the specific value x of t at this point. And this is very nice. Since we're integrating with respect to t, we can factor the t outside. And we get the area over tau of del of t minus tau. And of course, we know that the area under a delta function is what? We've already established that. That's equal to 1. So this is just equal to x of t. So we've kind of, at least in a hand-waving manner, proven the sifting property of the delta function. So this is pretty nice. We can do great and wonderful things with this. If we have the integral from minus infinity to infinity of x of t, or no, say e to the minus t squared times del of t dt, we know that that's equal to 1. Why is it equal to 1? Because e to the minus t squared evaluated at 0 is equal to 1. Now, convolution is commutative, right? If I were to ask you to prove this, how would you prove it? You could prove it in both cases by saying, look, the Fourier transform of this left side is x times u. I'm sorry, x times h. And what's the Fourier transform of the right side? It's h times x, right? So simply because multiplication is commutative, it turns out the convolution is also commutative. So the sifting property of the Dirac delta function can also be written as so that's just that's not very much mileage, but it's kind of interesting, I suppose. Here's a very important property of the Dirac delta in terms of convolution, and we're going to be using this quite a bit because it's a very powerful result. It says that if we have an x of t and we convolve it with an x of t minus tau as a function of t, we convolve it with a delta function centered at t is equal to tau. Man. What we get, this is an important geometrical interpretation, is we get x of t now centered at t is equal to tau. So again, any function convolved with a shifted delta function shifts the function to be centered where the Dirac delta was. And that's expressed in this expression right here, that if we take x of t and we convolve it with x of tau minus t, we end up with x of t minus tau. We end up with the function shifted over. How can we show that? Well, the x of t, maybe we should probably derive this here, x of t minus tau. We have to be very careful here. I'm going to do, no, I guess we won't. This is equal to the integral of x of c times delta of t minus c minus tau. Now you notice with the convolution integral, I've had to use a dummy variable c. Why did I have to use a dummy variable c? I couldn't use tau because we're using tau already and it has a different definition and we don't want to reuse tau again. We have to introduce a separate variable, a new variable. And so what do we have here? This is the integral of x of c, del of t minus tau minus c dc. One of the properties of the delta function is that it is even. Right? If you take a Dirac delta and you flip it around the y-axis, that Dirac delta hasn't changed very much, has it? It's an even function. So because it's an even function, we can multiply the argument here. We can multiply the argument by -1, and that's what we're going to do. X of c, since it's even, we're going to multiply this argument by -1, and we get c minus t minus tau dc, which is x of t minus tau. And this is by the sifting property, right? We get this function back at this variable. So from here to here, we've used the sifting property of the delta function. So this is a very valuable tool to put in your mind and to keep there, because this convolution idea of when you convolve something with a delta function, you get the something back centered where the delta function was at, is very powerful, thinking about Fourier analysis geometrically. And that's what we're trying to do. We're trying to do these things as geometrical as we possibly can. I think one of the big differences I've heard between engineers and mathematicians is mathematicians have these little pictures inside their minds, but they never tell you what they are. They have to write it down in all this highfalutin mathematics, and you have to follow the mathematics without knowledge of the pictures that they have in their minds. Engineers, on the other hand, and I think this is true with physicists, like to picture things, and we admit the pictures that we have in our minds. And I think by confessing to the pictures that we have in mind, we can teach better and have a better understanding of what's going on in the specific field. So that's the Dirac delta sifting property that allows you to replicate a function at a different place. If you want to replicate a function at a different place, you simply multiply by a Dirac delta centered at wherever that thing is. Cool thing about the delta function is that it has a Fourier transform of 1. In fact, this is very interesting that we have the sifting property can be written this way. That's the sifting property of the Dirac delta. Here's the interesting thing about the sifting property. Every algebra has a unit operator. What's the unit operator for addition? It's 0, right? You add something to 0 and you get 0. Multiplication, the unity operator is 1. You multiply something by 1, you get the same thing back. In convolution, the unit operator is the Dirac delta. If you convolve something with the Dirac delta, you get the same thing back. It is the unit operator for convolutional algebra. And that's kind of neat. And you can see that unit operator taking place here. If we convolve something with a delta function, we get the function back. This is, in fact, the sifting property, which we've written out in longhand here. Well, let's remember the sifting property to compute the Fourier transform. Delta function, if we plug into the Fourier transform, we get this expression, But what does the sifting property say? The sifting property says, okay, we have this delta function, so we get back what's ever left. We get back what's ever left at t is equal to 0, right? We get back whatever is left at t is equal to 0. If you think of the e to the j, you can't draw an e to the j 2 pi tu. But here's a basic idea. You have the complex sinusoid here. I don't know what it is. And you multiply it by a delta function. And what you're going to get is that complex sinusoid evaluated at the delta function at the origin at t is equal to 0. So if we evaluate the kernel at t is equal to 0, we get 1. So we can use the sifting property of the Dirac delta in order to define the Fourier transform of the Dirac delta. Now you'll notice we said that x of t convolved with h of t is equal to the Fourier transform. And we will always use capital letters. I think you've seen this, capital letters for the Fourier transform. So if we have an x of t convolved with a delta function, that's the same thing as, I'm sorry, this should be a double arrow here. This should Fourier transform to what? X of u times what? The Fourier transform of the delta function, which is 1. So we see that in the Fourier domain that 1 is the unity operator, and we see that corresponds to down here in the time domain that the delta function is the unit operator for the convolution operator. So we see it manifests itself in the Fourier domain as just multiplying by 1. So that's kind of interesting. Okay, I think this is what we saw before. The area is equal to 1. Yes, we've seen this before. And we talked about this as a limit also. The limit of this rectangle with the unit area always has a unit area. And as capital A goes to 0, we have 0 width, infinite height, area of 1. That's what one has to remember about the delta function besides some of its properties. Here's a Dirac delta scaling theorem. And this is very interesting. Delta of AT is equal to 1 over the magnitude of A times delta of T. Now, I don't know if we have the tools to prove this yet, but we can argue it through the Fourier transform or through the, not the Fourier transform, but the definition of the Dirac delta. Now, before we had a width of what? 1 over A and a height, I'm sorry, 1 over A and a height of A. And this went to what? A delta function, right? What would happen? What would be something that goes to delta of AT? Well, AT would be something that would have a width of A over A and it would have a height of A. I'm sorry. This would be 1 over AA. Remember, we said when we multiplied this, we shrunk it down by the factor. So here we're multiplying by a little a, so we're shrinking it down by a factor. So this would approach 1 over, I'm sorry, the delta of AT. Now the interesting thing here is no matter what the value of A is, what is the area of this thing? The area of this thing is 1 over A, correct? The area of this is 1 over A. So therefore, the integral of this should be 1 over a. And that's the same thing as 1 over a times the integral of delta of t, isn't it? So again, this thing would approach del of at. This would approach del of at. And the area there is equal to 1 over a, and that's exactly the same as 1 over a times the area of a delta function. And with this, we argue that since these are the same, that this is true. Now, this is not a proof. This is a lot of hand waving because we're not defining the Dirac delta as a distribution. We're defining it intuitively as this limit of the rectangle. I'm going to ask you to do a problem. This is very interesting. What is delta of question? Nope, just a microphone moving. What do you think the delta function of the delta of a function is? And yes, believe it or not, these sort of things happen. They happen in communication theory. It's very, very interesting. Let's talk about the delta function of the cosine of t, or in general, the delta function of a general g of t. It's actually not that difficult. If you the only time the delta function is defined is when its argument is 0, right? I mean, delta t is only dangerous when t is equal to 0. So that's the only time that we have danger here. So del of g of t is going to be something interesting only when g of t is equal to 0. So if we have a g of t like this, if we have a g of t like this, the only thing we have to worry about is this crossing here. Everything else is going to be 0. So del of g of t something's going to happen here. We're going to get some sort of delta t here. But for the rest of the value, that's going to be equal to 0, isn't it? And so you guys look like you've had enough. I'll give you a little hint. If you take a microscope and you zoom in on this, what do you get? You get some value of tau. This is g of t here. But you get some value of tau where g of tau is equal to 0, right? If we blow this up enough, can't we approximate this by a slope of, say, a of t minus tau? That is, if we get our microscope and we look at this point of the 0 crossing and we blow it up enough, that's going to be a line in general. And that line is going to have an equation, a of t minus tau. And if we, what is a equal to? Isn't that related to the derivative of g at the point tau? Yeah, it is. It's related to the derivative. So I'm going to let you scratch your heads over that one. It's going to be a problem which I assign you. I believe that the solution is in the book, and we'll assign that for next time. So with that, let me ask if there's any questions, and we will proceed next time. Let me see what we're going to do next time. This is exciting. Whoops, I'm going the wrong way. Well, I have lost all of my stuff here. Okay, well, I guess this is a good point to end the lecture since I've lost all of my stuff. So with that, are there any questions? Did everybody get the homework okay? Were there any problems on the review questions at all?
Dr. Marks, I had a question, and I guess I should have asked this before, but on the spreadsheet, you said due on the 31st, right?
Yes,
yeah,
Monday.
And it was right next to problems 1 and 2, but it wasn't next to where it said review. So I don't know if you wanted just to do review and the homework.
No, I do not want you to write anything down for the reviews, just the homework.
Okay, got it.
Because I believe that if you look at the reviews, there's no reason for you to copy down the answers in the book and hand those in.
Okay, so you won't expect us to return those in, but they're just for our benefit, basically.
Yeah, they are for your benefit and for discussion. And it's important you look at those and at least have an understanding of how those problems are worked. Because it's like anything. In order to become familiar with this stuff, you have to expose yourself to it quite a bit. So that's hopefully what we're doing.
Will do. Thank you.
Okay. Sorry for the ambiguity. Hopefully that's cleared now. Any other questions? Okay, if not, we'll see you Thursday, and go to the spreadsheet, and we'll have some more comments and things of that sort. So thank you, and be of good cheer.
Thank you.